I will affirm the resolution. This House believes the base language AI uses is topological. Opening statement. The nature of how large language models, LLMs, represent and process language is a complex and evolving area of research. While we don't have a complete, definitive understanding, I argue that the underlying structure, the base language, that LLMs utilize, possesses significant topological characteristics. This isn't to say it's purely topological in the strict mathematical sense, but that topological concepts provide a powerful and insightful framework for understanding how LLMs capture meaning and relationships between words and concepts. It's about the shape of the language's representation within the model. Arguments. High-dimensional vector embeddings. LLMs fundamentally rely on high-dimensional vector embeddings, like word, 2vec, glove, or those learned within transformers. These embeddings represent words, phrases, and even entire sentences as points in a high-dimensional vector space. The distances and relative positions of these points are crucial. This is inherently a topological concept. Topology is concerned with properties that are preserved under continuous deformations, stretching, bending, but not tearing or gluing. The closeness of embeddings, measured by cosine similarity, or other metrics, reflects semantic similarity. Small changes in meaning should, ideally, correspond to small, continuous movements in the embedding space. Manifold hypothesis. The manifold hypothesis in machine learning suggests that real-world high-dimensional data, like language data, tends to lie on or near a lower-dimensional manifold embedded within the high-dimensional space. This means that while the embeddings are represented in, say, a 1024-dimensional space, the meaningful variations in those embeddings can be captured by a much smaller number of underlying dimensions that define a curved, complex surface, the manifold. This is a fundamentally topological idea. The manifold is a topological space. The LLM, in effect, learns to navigate this manifold. Neighborhoods and continuity of meaning. The notion of neighborhoods is central to topology. In the context of LLM embeddings, words with similar meanings should reside in the same neighborhood of the embedding space. Moving smoothly within a neighborhood should correspond to gradual shifts in meaning. For example, moving from cat to feline to animal represents a continuous, though potentially nonlinear, path through the embedding space, reflecting a continuous change in semantic generality. This continuity is a key topological property. If a small change in the input text leads to a massive jump in the embedding space, the representation wouldn't be topologically sound, and the LLM would likely perform poorly. Hierarchical relationships as nested topological structures. Language exhibits hierarchical relationships. For example, dog is a type of mammal, which is a type of animal. These relationships can be thought of as nested topological structures, with more specific concepts residing within the neighborhoods of more general concepts. This kind of hierarchical organization can be represented using structures like topological trees or graphs, where proximity and connectivity reflect semantic relationships. Contextual embeddings and dynamic topology. Modern LLMs use contextual embeddings, e.g. Bert, Roberta. This means the embedding of a word changes depending on the surrounding text. This can be viewed as a dynamic topology. The shape of the language representation isn't fixed, it deforms and adapts based on the context. Imagine the manifold flexing and changing shape as the LLM processes different sentences. This is still fundamentally topological, but it's a topology that evolves with the input. Loss functions and topological optimization. The training process of LLMs involves optimizing a loss function. This optimization can be interpreted as finding the best topological configuration of the embeddings, the arrangement that minimizes the loss, which often relates to predicting the next word or performing some other language-related task. The loss function, implicitly or explicitly, encourages the embedding space to have desirable topological properties, smoothness, meaningful neighborhoods, etc. Rebuttals to anticipated opposing arguments. LLMs are just statistical models, not geometric ones. While LLMs are trained using statistical methods, the representation they learn is inherently geometric and topological. Statistics is the tool, but the resulting structure has topological properties. Topology is about discrete structures. LLMs use continuous vectors. This is a misunderstanding of topology. Topology deals with both discrete and continuous spaces. The concept of continuity is central to topology. We don't know the exact shape of the embedding space true, but we can analyze its properties and observe behaviors that strongly suggest a topological structure. The success of LLMs in capturing nuanced meaning provides indirect evidence for the underlying topological nature of their representations. The representation isn't perfectly topological, I agree. There might be imperfections and deviations from a perfectly smooth manifold. However, the dominant characteristics and the guiding principles of the representation are fundamentally topological. Closing statement: the base language that LLMs use isn't just a collection of statistical correlations. It's a high-dimensional, dynamic, and likely topologically complex structure. The embeddings, their relationships, the manifold they inhabit, and the way meaning changes continuously within this space all point towards a fundamentally topological organization. While further research is needed to fully characterize this topology, the evidence strongly supports the claim that topological concepts are essential for understanding how LLMs represent and process language. The shape of language, as learned by the AI, is key to its power.